Hello guys, in the last class we were discussing practical transformer on no load. We left in the half. We discussed till I naught is having two components, that is IC as well as IM, and IC is called as wattful component or core loss component, which is utilized to supply the core losses, and IC was equal to 0 for ideal transformers. So I naught was equal to IM in ideal transformer, but here IC is not equal to 0 since we are dealing with respect to practical transformer. So IC will be present here. So I naught is equal to IC plus IM. So IC is all over, that is a core loss component or power or wattful component, or also can call as power component as well. Second one is IM, a purely reactive component, is called as magnetizing component. Okay, IM is called as magnetizing component, which requires no load current to produce the flux, so as to magnetize the core to pass the flux from one electrical circuit to the other electric circuit, that the current is utilized. So that is called as magnetizing component. Usually the losses is not accounted, so it is called as wattless component. Okay, so there are no such losses since no load current will be very little, and again loss due to that is very negligible, ignorable. So we are not considering it as wattful, we are considering it as wattless component, as whatever current is drawn, that is IM is drawn, it is utilized to produce the flux in the core with respect from one electric circuit to the another electric circuit. So it is called as wattless component, which is used to produce the flux. Okay, this is what I told you. If you want to add vector addition, means I naught can be written as IM plus IC or IC plus IM, and this represent vector symbol. Okay, the dash above the layer symbols. Okay, now coming to this practical transformer on no load. This is your phasor diagram. In ideal transformer, you can see I naught was lying on IM. Yes or not? Let me show you once again. You can see I naught means nothing but, I told you, I1 is nothing but equal to I naught, and I naught is equal to IM, as IC is equal to 0. If you want means you can write I naught as well here. Okay, but now it is not so. I naught is making certain angle phi naught with respect to V1. Okay, I naught is making at an angle phi naught with respect to V1. Before coming to I naught, let us anyhow we know that I naught is divided into two components. One is IC as well as IM. IC is called as core loss component, and IM is called magnetizing component. And we know that flux we have taken it as reference over here in the horizontal line. The same thing we took here also in ideal transformer, flux. So here also it will be same. And we know that IM is responsible for producing flux. So IM is in phase with the flux phi. Okay. Now IC. Okay, IM is over IC. IC is the current which will supply the core loss component core loss. Okay, it will supply the core loss. And what happens? IC will be in phase with the V1. IC will be in phase with the V1. So IC and V1 lie on the same phasor. IC and V1 lie on the same phasor. Okay. So due to this, the resultant of IC and IM is nothing but what? I naught. Okay. IC and IM resultant is what? I naught, and I naught makes angle phi naught with respect to V1. So you can call it as no load power factor. Okay, you can call it as what? No load power factor angle, to be precise. Cos phi naught means no load power factor, and phi naught is no load power factor angle. Okay. So what happens? That's why the reason I am going to get certain angle here. I naught doesn't lie over IM, or I naught doesn't lie over IC, since we know that in a practical transformer, due to winding resistance, I naught will be no more at 90 degree with respect to V1. Okay, it is a combination of resistance as well as inductance. So what happens there? And so it's not a pure inductance also. If it was pure inductance, means I naught would be lying on here. Yes or not? As current and voltage always have 90 degree with respect to each other for pure inductance, as it happened for our ideal case, ideal transformer case. But now it is not so. The resistance will be always present in the windings of the transformer. So what happens? Instead of making at an angle 90 degree with respect to V1, I naught will make angle phi naught with respect to V1. Okay, and anyhow E1, E2, you know, these are anti-phase with respect to V1, and E1 and E2 magnitude depends upon the number of windings you do on the primary as well as secondary side. And here it will be same. Okay, only one thing you need to remember is IC as well as I naught. That is what different between your ideal this. Okay, I am in here, it is over here, IC will come over here and I naught will come over here. It makes an angle phi naught. That is what difference between ideal transformer as well as practical transformer on no load condition. And coming to this, how this came, I am equal to I naught sin phi naught. Very simple, can apply your trigonometry rule over here. Sin phi naught means what? It is opposite by hypotenuse, right? This is your opposite, and this is your hypotenuse, and this is your base. Okay, and also you can call it as adjacent. So opposite by hypotenuse. See, here to here, what is the distance? Sin here, opposite by hypotenuse means here to here distance is Im. Okay, so Im, and what about this distance? Opposite by hypotenuse, and this distance is I naught. So what happens? Im by I naught. Im by I naught is equal to sin phi naught. Okay, Im by I naught equal to sin phi naught, or else you can write it as Im is equal to I naught sin phi naught. Why I am writing like this? Because since I need to calculate the magnetizing current to be precise, so we are doing like this to calculate Im. If I know power factor angle, that is no load power factor angle. If I know the no load current, then I can easily calculate what? Magnetizing current. How much current is utilized to magnetize the core. And now coming to this, what about IC? If I want to know this IC means I have to go for cos. Since I was in need of to know the value of Im, so I went for sin. Now I need to go with the IC. Then IC means what will come here? Yes, IC will be your adjacent. So I need to go with the cos. IC means how cos phi naught means how much? It is adjacent by hypotenuse or base by hypotenuse. So your adjacent is value is what? IC. Okay, and hypotenuse value is I naught. So IC by I naught is equal to cos phi naught, or else you can write it as IC equal to I naught cos phi naught. Okay, and anyhow we know that I naught vector I naught is equal to vector addition of Im plus IC. If I want to take only magnitudes, in sense what I have to do? I have to take mod on both sides. When you take mod on both sides, it will be what? I naught square equal to Im square plus IC square. And again, if I remove the square root, the square over here means square root will come on the right side. That is square root of I square M plus I square C. Okay. Now we know that while phi naught is the no load power factor angle, and similarly here also we will do the same as we did the thing over here. That is no load power input for ideal transformer was what? V1 I1 cosine of angle between V1 as well as In, and anyhow angle between V1 and In was 90 degrees, so cos 90 is equal to, anyhow it is 0 cosine of, this is the formula for no load input. So no load input was equal to 0 for ideal transformer, but here let me check, or let me see whether it is 0 or not. Same formula here, V1 I1, here instead of taking I1 here I am going to take it as I naught, because I naught is a combination of IC and Im, so I will take it as I naught here. So V1 I naught cos phi naught. So what happens here? We know that I naught is equal to IC plus Im. Since Im is very small, so we are ignoring it to or making it to 0. But IC is your wattful component and Im is your wattless component. I am terminating Im as 0, but IC I will consider since it is supplying the losses. Okay. So what happens? I naught is equal to IC plus Im, in sense what happens? So Im will go off. And what about cos phi naught? How it gone? So what happens during no load and all, this power factor angle will be what? Very less. Okay, phi naught will be very small. We know that cos of small means it will be approximately, small angle means it will be approximately equal to 1. So cos of small angle, can check in the calculator as well. What happens? It will be approximately equal to 1. So what happens? I naught becomes IC, as I told Im is equal to 0. Means we are all approximating over here. Okay, we are all approximating just for the sake of formula purpose. So what happens? I naught becomes IC, whereas cos phi naught be equal to almost equal to 1. So the formula will be V1 into IC. But it was 0 in ideal transformer, but practical transformer it is not so. Okay. So what we came to know that W naught is equal to, or else you can write once again this V1 I naught cos phi naught. Whatever power is drawn is utilized to produce supply the iron losses. Okay, iron loss. So V1 I naught cos phi naught is equal to Pi is equal to iron loss. So we can also call this particular no load input as iron loss, that is Pi is equal to iron loss. And problems and all we'll discuss the coming session as well. First we shall discuss only theory. Now it's time for transformer on load. what happens when load is connected to the transformer, or also it is called as MMF balancing on load condition. Okay, remember till now whatever we discussed was with respect to no load, either it is practical transformer or ideal transformer. Now we are going to discuss your practical transformer with respect to load condition, how your transformer behaves when actual load is applied on the secondary side. Okay, you may get question on this, discuss transformer on load or discuss MMF balancing on load. Okay, so before getting into this, let us know what exactly MMF is. Okay, MMF is very similar to your EMF, where your EMF drives current or electrical charge in the circuit. In similar to that, your magnetomotive force drives magnetic flux in the circuit. Okay, and one more thing, your MMF is characterized by the formula ampere turns, that is number of turns into current. So it is product of number of turns N and current. So if I want to calculate MMF in the primary circuit, then it will be what? N1 into I1. If I want to calculate MMF in the secondary circuit, then it will be N2 into I2. Where this is a primary circuit where I am going to connect the supply, AC supply, and this is secondary circuit, I am going to connect the load. Okay. Now let us dig into this. That is transformer on load, MMF balancing on load. Why it is called as MMF balancing? Let us see. After completion of this topic, you will understand why it is called as MMF balancing. Now, anyhow they have connected load over here. So for as of now, we are going to consider this as open circuit, means assume that there is no any load connected here. Okay, and if there is no any load connected, then what happens? I2 will be equal to 0. So when I give supply here in the primary side, what happens? Current I1 starts to flow in the circuit and it completes the path here. Yes or not? Yes. Any of them not shown? I should write here I1 here. Okay. I1 completes the path in the closed circuit, and due to this what happens? Your main flux, this is the dotted line which they have shown at the top here, and this is nothing but your main flux. As per the Faraday's electromagnetic induction, we know that whenever magnetic flux linked to the circuit changes and EMF is induced in the circuit, so what happens? Your magnetic flux is drive in the closed path due to the MMF and all, due to N1 and I1, because MMF is equal to N1 into I1. Due to this what happens? Your flux is driven in the magnetic core. And what about the second dotted line? They have called it as secondary flux phi 2, and now we are going to assume it as again 0, because whatever flux phi 2 is produced, that is because of I2. But now initially I told, right, what I told assume there is no load connected and I2 is equal to 0. If I2 is equal to 0, then secondary flux will be also equal to 0, so there will be no any dotted line. Clear? Okay, so no load connected, I2 is 0 as well as secondary flux is 0. So when I give supply, what happens? I1 flows in the primary circuit, it produces its own flux, and the flux is driven in the magnetic core. Okay, that is called as main flux phi. Fine. So this is the initial understanding. Now any of the topic itself is based on transformer on load. So now with this knowledge, we are going to add the transformer on load condition to this existing one with that knowledge. Now what I am going to do is I am going to connect the load, like as you are seeing on your screen. So when I connect load here, then what happens? Obviously this path is closed, and if the path is closed, means obviously what happens? Some amount of current will be drawn from the secondary circuit, that is I2. We are calling it as I2. I2 is drawn from this secondary circuit, so I2 completes its path. So when I2 starts to flow, then what happens? There flows secondary flux phi 2 in the circuit. Okay, you can see secondary flux is flowing in the magnetic core here. And one interesting thing what you can see over here is the main flux direction as well as secondary flux direction are what? Opposite to each other. Yes or not? You can see main flux is going from left to right. And what about secondary flux? It is going from right to left. So both are what? Opposite in each other. Okay.